Hello, welcome back to Bare Metal Machine. I'm Jeff Audia. Several of the videos I've made in the past feature parts being machined with what I call the integrated rotary table. Now, I thought I could do a better job at explaining how this rotary table system works without doing any machining and without all the chips and coolant and fixture and other stuff in the way. So let me just hit the reset button and try to explain more clearly how this system works. This is an ordinary, commercially available Phase 2 brand 8-inch precision rotary table. And all I've done is take the hand crank and the vernier scale off and adapt a stepper motor to it. And even though it's an 8-inch rotary table, the perfect size for a Bridgeport scale machine, I put this subplate on here myself. This is a 10-inch diameter subplate because I consider the working envelope of this table to be actually more like 10 inches, not 8 inches. Okay, so this is not part of the table as it comes, when you purchase one. I've made this subplate myself. The rotary table is powered and controlled by the electronics inside this electrical box. Let me show you the insides. Okay, let's take a look inside here. What we have here is a DC power supply, and this is the stepper motor driver. This is what actually delivers the current to the motor's windings to make it step in either direction. And this is a computer circuit board, and this is the brains of the system. And it has a digital interface to the outside world, and for instance this goes to the Cartesian display or any other computer control system. This is a USB interface, and this could go to, say, a laptop, so you could have manual control over the rotary table. Now, this computer board is necessary because clearly the stepper motor and the power supply, they don't know what angles are. They don't know the ratio of the worm gear or anything like that. So something has to be responsible for acceleration and deceleration, backlash control, indexing, driving the table to particular angles that you command it to go to. And so this is the only component in this whole system that I actually made. Everything else you see here, the enclosure, the power supply, the stepper motor driver, these are all off-the-shelf components. This is the only custom component that I actually made. Okay, let me just go to the rear of the Cartesian display unit here. And this yellow cable here, this is the cable that I was pointing to on that computer board inside the rotary table controller box. And it goes to the Cartesian display's auxiliary serial interface. Okay? These other two connections, these are just your scale inputs. Okay, so as it relates to using the rotary table with the Cartesian display, there's really very little you can do without finding the center of rotation first. Okay, so you got to pick up the center of rotation of the rotary table and then zero out your DRO and then zero out the Cartesian display. Okay, let me reintroduce this part that was featured in another video. And this part, it was made on this system, on this rotary table also, except that it was mounted on a fixture on this subplate here. And I just picked this part because it has lots of angles and features on it that are going to allow me to illustrate my point here. Except I'm not going to use the part itself. I'm going to use this one-to-one paper template of the same part, and I'm going to just tape it down any old arbitrary position on the subplate here. Okay, there we go. Okay, so the next thing you have to do in a setup like this, after you found the center of rotation, which we did a minute ago, is you have to find C-axis 0. So usually, like on a fixture, you'd have some milled surface, and you would indicate that milled surface to be parallel to the x-axis or y-axis or whatever it happens to be. But since I don't have a fixture, and all I have is this template, I happen to know from the CAD drawing that these two holes are parallel to the x-axis. So if I could just find the angle that makes these two holes parallel to the x-axis and then set the table at C-axis 0, I'll be off to the races. Okay, so here's what we're going to do, is I'm going to just use my pointer, and I'm going to point to the center of this first hole here. Okay. Yeah, it looks pretty good. Now, you've seen me do this a bunch of times with the Cartesian display. I go to rotary, auto 0, locate first point, hit OK. That's the first point, OK. Now locate second point, hit OK. And that looks pretty good right there. We're just doing this by eye. It'll be close enough. Okay, hit OK. Now it's computed the angle that it needs to move the C-axis, and I'm going to check it now. So I'm going to put that on the right on center. Okay, good. And there it is. It looks like it's pretty close. So it figured out the angle to move the C-axis to make these parallel to the X-axis, and it set it to 0. This is now 0 degrees, and all these other angles are relative to 0 degrees. And of course, remember, I didn't have to do any math or key in any data. Okay, now the next thing we have to do is we have to tell the Cartesian display what is the distance and direction from the center of rotation, the physical center of rotation that we found earlier, to the geometric origin of the part geometry, which is this point right here. So on the CAD drawing, this point is 0, 0 of all this geometry. Okay, so all I need to do is point to that location. Now on the fixture, of course, I'd be indicating a hole here. Right, there's like a 1-inch diameter hole in the fixture that represents this location. And what I would be doing is I'd be using my indicator, and I would indicate that hole, and I would call that, my part geometry origin. Okay, so, this looks pretty good by eye. Now remember, our pointer is pointing right here to 0, 0 of the part geometry. And presumably that would have been a hole in our fixture that we would have indicated in, okay? So we're pointing right here, okay? But we already know that the physical center of rotation is somewhere other than where the origin of the geometry is, okay? So what we're going to do is we need to translate the part, the distance and direction from the actual geometric origin to the physical center of rotation. So we do that with menu, translate to tool position, right? That's where our pointer is right now. So I hit OK. Okay, and see it's translating this much, a little bit in X and quite a bit in Y. Okay, now look what happened to the image here. It has shifted it, over in X and up in Y. And now these crosshairs here, the X and Y axis, that's the physical center of rotation of the rotary table. But up here where the tool is, where that little point is, that's the geometric origin of all this geometry. Okay, so now the Cartesian display has what it needs so that no matter where we rotate the table, everything's going to fall right into place because we've set C-axis 0, right? These two holes are parallel to the X-axis, so now we're at C equals 0 degrees, and we've translated to the physical location of the origin of the part geometry. Right, remember on the fixture that would have been a hole that we would have trammed in. Okay, so we should be good to go. Okay, so now everything's set. I should be able to navigate to any feature on this part and point right to it. So let's go to radar, holes. Okay, so the first hole, circle 1, that's in red. So let me navigate to that hole. Okay. Watch the radar now. So it's telling me I got to go up 45 and Y. I'm not going to get too fussy about these. Okay, that's close enough. Now I got to go negative in X. Oops, I'm sorry, positive. Right, that's close enough. Now, okay, so our tool is right over that hole according to the Cartesian display. And in fact, you can see our pointer is pointing right at the center line of that hole. Okay, but remember that the whole point of this demonstration is that I can now rotate the part geometry to any angle I like, and all the geometry is going to be precisely where it needs to be. Okay, so let's just try it. I'll go to Menu, Rotate Part. Let's go to minus 23.518 degrees, just some arbitrary angle. Okay. Okay, now the table's taken off. Now I should be able to navigate right back to that hole, and I should be pointing at it again precisely. Watch the radar. Seeing I got to go up in Y, about 20 thousandths, 30 thousandths. Okay, close enough. Okay, now positive an X a little bit. Okay, close enough to 0, 0. Okay, now, okay, it's Cartesian display is saying I'm pointing directly at that hole. Now, what does it look like in reality? And the pointer now is indeed pointing directly at the center line of that hole. Let's try something else. Let's go to radar normal mode. Okay, I'm going to find line 6. Line 6 is this vertical line here. Or rather, it's about to be vertical. Okay. Okay, so you see line 6, that's on radar, it's in red. Now I'm going to go to menu, and let's say I wanted that line to be parallel to the y-axis so I could machine along it. So I'm going to pick a line with y. Okay, you should have heard the table take off right there. So now, that line is indeed right parallel to the y-axis. And now let's take a look down on our template. Okay, so let me navigate over to that line. Okay, so I'm pointing right on that line. And as I move the y-axis alone, you can see that line is parallel to the y-axis. Okay? Now let's try something different. Let me take out the pointer, and I'm going to swap it for this pin, which is 3/8 of an inch in diameter, and that will represent, say, an end mill. Of course, we're never holding an end mill in a drill chuck, are we? Now let me rotate the part to yet another arbitrary angle. Rotate part 41.258 degrees. Okay. Now I'll change the tool to be 3/8. Okay. Now I'm going to maneuver the tool into, I'm going to go into that little corner right there. Okay. Zoom in. Right, way in. Now, of course, I could be using the radar to get myself exactly tangent to these lines. I'm just going to do it by eye just to make a point here. Let me just get as close as I can by eye. And that looks pretty good right there. Now let me move my little mock end mill down into the template here. And you can see it is right in that corner where it should be. It couldn't do that unless the math was exactly right. All right, one last example. Reset view. What if I wanted to machine along this line here? Okay. What I'm going to do is I'm going to turn the radar on, radar normal, and I happen to know that's line 5. Line 5. Enter. Okay, so now line 5 is on radar. Now I want to go menu, and let's say I want to machine along the y-axis. Align with y. Okay. Okay, so the table just moved. Now I can simply move my cutter into position. Right, let's say I'm getting ready to make that cut. And I want to use the radar to get myself exactly on that line, right? So I'm going to move, watch the radar now, distance. Okay. Let's say that's close enough. Okay, now I'm exactly on that line. And as you can see, I am exactly on that line. Now moving only the y-axis, I can machine along that line because it is parallel to the y-axis. Okay, the Cartesian display computed the angle that was necessary to make this line parallel to the y-axis. Now, I don't know the angle. It tells me the angle. You can see it on the screen, but I never needed to know the angle in the first place. Okay, it computes the angle and it communicates that angle to the rotary table controller. The rotary table controller does the rest. Well, I hope this little demonstration clarified what I mean by the integrated rotary table. Essentially, you can take your workpiece and you can mount it on the rotary table in almost any arbitrary way you like. And then after you have found the center of rotation, you would next pick some feature on the fixture or the part or a vice jaw, anything that you could indicate to be parallel to the x-axis. And then that sets the c-axis angle to 0. Next, you simply find the feature on your part that represents your geometric origin. So it might be a hole, you might use an edge finder to pick up a corner of the part or something like that, whatever your CAD model has as 0, 0. And then you just with a menu pick, you saw me use translate to tool position. I never keyed in any data. I never wrote anything down. I never had to do any math or anything like that. Everything was done at the touch of a button from start to finish. And then, I demonstrated how no matter where I moved the rotary table, all the geometry tracked precisely. And so no matter where you move it, the geometry, everything is right where it needs to be. And so that's the magic of the rotary table and how it integrates with the Cartesian display. Now, one thing I'd like to add is that the rotary table is not part of the Cartesian display. It's a separate standalone product. You could control the rotary table with any computer over a serial interface, through binary or an ASCII terminal, things like that. And it's a standalone product. The thing is that since I developed both of these things, I was obliged to make them talk to one another. But I publish the interface. Anyone can talk to the rotary table controller and make it do whatever you like. Another thing I want to clarify is that you don't need to have the rotary table to use the Cartesian display, right? The Cartesian display and the rotary table are two separate systems. The only reason that most of my videos feature the rotary table also is because they tend to be more interesting parts to look at. And I try to make my videos as compact as possible and show as much information as possible. But I use the Cartesian display routinely, and I never use the rotary table on probably most of the things I make around here. So I just want to make that clear. You don't need the rotary table to use the Cartesian display.